We're going to talk about linear transformations and matrices. You know, some transformations are a little more obscure, like clean cut Mr. Kelly here in his early 30s to Christmas tree Mr. Kelly here with the goatee. Why people change, I don't know, but look, it's a good look, Mr. Kelly. Hope you bring it back soon. All right, let's take a look at this. So we are going to apply a transformation. All right, now we're going to talk a little bit more about this, but this is the real numbers to the real numbers with two coordinates, right? X and Y, X and Y. Sometimes most of the times in our lives, we've been talking about the real numbers with just R. Well, that's one set. That's when we talk about one thing at a time. Today, we're going to talk about two things at a time, X and a Y. So we have two things taken at a time. And we're going to apply this transformation, which is a matrix, all right, matrix A, and it is identified as -1, 0, 0, 1. All right, let's see what happens when we actually go through this and apply our matrix. So the first thing I want to do is I'm going to have my matrix, -1, 0, and 0, 1, my transformation, and I'm going to multiply it by my vector. So in this case, I have vector u. Right? Now, vector u, let's graph vector u over here. Vector u is 4 on the x, 1 on the y. So this is our vector this way. All right? And we'll label that vector u. Okay? We understand because this is a coordinate plane, we have 2 points at one time. This could be a vector. This could be a point, right? All right. So let's apply that transformation and see what happens when we multiply our vectors. So first of all, we have an x-coordinate, we have a y-coordinate. And just so we're clear, when we multiply a 2 by 2 and a 2 by 1, these match. So we're going to get a 2 by 1. All right, this should be pretty easy. -1 times 4 is -4, plus 0 times 1 is 0, so this is just going to be -4. My second element here is row 2, column 1. So row 2 is 0 times 4, that's 0, plus 1 times 1 is 1. So my new vector is now going to be -4, 1. All right, and we write that as the vector of u transformed. All right, the transformation of u. I'm going to graph that up here, -4, 1. Drawing straight lines is, of course, obviously not one of my strong suits. I'm really sorry about that. So now we have that. We have a u, vector u, and we have the transformation of u. All right, let's go back and do another one. So now we have the vector -2, 3. So again, we're going to apply this transformation, -1, 0, 0, 1, to our vector, x-coordinate, y-coordinate. Let's see what we get. Well, first of all, let's plot it. -2, 3 is right here. So that is my vector v. All right, that's my original vector. Let's see what happens when I transform it. See what we get. Of course, I'm going to get a 2 by 1. So I'm doing first row, first column. So -1 times -2 is +2 plus 0. All right, then my second row, first column is 0 times -2 plus 1 times 3. Boom, 2, 3. I can plot that one over here. And bada binga bada boom, there we have it. The transformation of V right there. All right, now, if you have a keen eye, you've noticed something. These transformations right here, they are reflections in the y-axis. So when it describes the transformation, it's a reflection in the y-axis. In other words, it's a horizontal translation, isn't it? All right. It says, what is a general transformation that occurs? Well, I'm going to do the same thing. I'm going to assume now that instead of my vector being -2, 3 or 4, 1, my vector is xy. So let's do it. I have -1, 0. This is my transformation vector, matrix, excuse me. And I'm going to multiply it by x and y. So here we go. -1 times x plus 0 times y. So that's just -x. 0 times x plus 1 times y is y. So you can see my resulting vector is negative x, y. So now we know that in the future, this transformation matrix really takes it and I get the opposite value of x and the same y value. Thus, therefore, it is going to transform or reflect in the y-axis. Very nice. All right, it's time for a little bit boring talk here, but this is important to understand. What are we talking about? If the domain of a function f, so we have a function, is all real numbers to a certain power, meaning that's how many coordinates we could have, how many dimensions, right? We have 2 dimensions, we plot on an x and y. We have 3, we could have an x, y, and z graph. As you get into much more complicated math, you could have many, many more. So if my domain is all real numbers to the n power, and the range, my outputs, is all real numbers to the m power, where m and n could be equal, then f is called a map or transformation from Rn to Rm. So in other words, I'm taking my input function and I'm mapping it to something else. It transforms likewise. All right, now, please understand, we're going to be working with just one specific area. That is going to be R2 to, not D2, sorry, but R2 to R2. So we're going to be working on coordinates, right? And you need to understand, we have an x and a y axis. We could represent things a couple of ways. If I have 2, 1, that is a point. We know it's a point. But now we also know I could say 3, 4, 3 up 4. I could also represent that as a vector in 2 dimensions, all right? So we're going to be dealing with transformations that take things from R2 to R2. We're not going further than that, all right, in this lesson. As you continue your math career, you probably will go further than that, but right now this is just a new thing, okay? Now there's a couple of conditions down here for this to be true. For a function to be a linear transformation, it has to maintain the following criteria. Number 1, vector addition under the transformation has to remain. So when I add the 2 vectors together and then transform it, it has to equal the transformation of one vector plus the transformation of the other vector. All right, so again, I add the vectors together, then I transform it. That needs to be the same as whether I transform the vectors first and add them together. All right, likewise, scalar multiplication also has to be true. So if I scale the transformed vector, it needs to be the same as if I had scaled it and then transformed it. Kind of sounds tricky. Let's try one. All right. So I just have this up here again, just so we could all see, but this is on your notes already. Now this is the transformation we found in example 1. All right, we found that it was negative x, y. All right, so the first thing that we have to understand is, does this hold where I can add my vectors together and then transform them? All right, and then it's the same as the transformation of one plus the transformation of the other. So let's do a couple of things. First of all, let us define a few things. Vector u, we're going to call A1, B1, okay? So that would be the matrix A1, B1. And likewise, vector v, we're going to call A2, B2. Creative. All right, and that'll give us the matrix A2, B2. Very good. All right, so we need to see if this is true. So is the transformation of u plus v equal to the transformation of u plus the transformation of v? So the first thing over here is we're going to add our vectors together. All right, then we're going to transform them. So what do we get when we add our vectors together? So we are going to add A1, B1 plus A2, B2. All right. And what does that give us? Oh, by the way, this is a big question mark. Does it equal it? Let's see. That gives us, when we add those, we add corresponding elements, A1 plus A2 over B1 plus B2. All right. Now we need to transform that. All right. Let's transform that. What does our transformation say? We take the opposite of the x, right? And we take the y. So in other words, the opposite of our x and the y. So here we go. We're going to transform this. That would result in the opposite of a1 plus a2 and exactly our y. So what is the opposite of this? That would give us negative a1 plus negative a2 over b1 plus b2. All right, now why did I use variables and not numbers? Well, the reason I use variables and not numbers is because it could work for certain numbers, but not all numbers. When we do and prove it with variables, it's got to work for everything. All right, so let's come over here. We're going to do the transformation of u. So the transformation of u, again, was a1, b1. So when I transform it, that is going to transform into negative a1, b1. And the transformation of v is going to be negative a2, b2. Now let's see, do those equal each other? Negative a1 plus negative a2, when I add those together, I get that. And b1 plus b2, I get this. And woo, look at that. They do equal each other, so that part is good. Way to go. So that satisfies vector addition under the transformation. It holds, it's maintained. All right, now let's see if we can do scalar multiplication. So again, we want to see, is the transformation when I scale my vector equal to scaling, when I transform it first. All right, so let's see here. Over here, I'm going to multiply u by c. So that gives me ca1 and cb1, right? That is the transformation I get. All right, or that's my scalar. So now let's perform my transformation. So that is going to result in the opposite of that. So negative ca1 and cb1. All right, that's very nice. So let's go over here. So now I need to do my transformation first. So when I transform this first, I have negative a1 and b1. And when I scale it, I multiply that inside, and I have negative ca1 and cb1. And are those equal? Yes, they are. So scalar multiplication is also upheld. Awesome. All right, this one's a little bit more challenging, and so I would like you to try this one on your own, all right? See if this maintains our two conditions for it to be a linear transformation. Just pause the video, try your best, and then I'll walk you through what I did, all right? All right, we have a lot to dive in on this one. First of all, I'm going to be adding x plus y, my x and y coordinates, and then I'm squaring my x coordinates. So let's take a look. Does the transformation of my two vectors added together equal the transformation of my first vector plus the transformation of my second vector? Let's do this side first. So the transformation of u is x plus y, so a1 plus b1. Then I have on the bottom x squared, so my a1 squared. So over here I have ax plus y, a2 plus b2, and then on the bottom I have a2 squared. All right, when I add those together, I have a1 plus b1 plus a2 plus b2. On the bottom I have a1 squared plus a2 squared. When we come over here, I'm going to add the vectors up first, so I get a1 plus a2 and b1 plus b2. So now, when I add my x's is a1 plus a2 and b1 plus b2. Well, that right there, a1, a2, b1, b, that's the same thing I have on the top. On the bottom, I'm squaring my x. I have a1 plus a2, that's my x, I have to square it. Now, remember, squaring this does not mean a1 squared and a2 squared. It means a1 plus a2 times a1 times a2. which equals a1 squared plus 2a1a2 plus a2 squared. And that is not the same. So this does not hold up. So right now I already know it's not a linear transformation. It doesn't work here. But let's take a look to see if the scalar multiplication works. All right, so I'm going to put my scalar in first, c times a1, c times b1, do my transformation. So I'm multiplying my x and my y here. So ca1 and cb1, and I'm squaring my bottom one. ca1 squared, so I square both of those. This is different than this because this has an addition sign. This is just multiplication, so I square all these factors. That's c squared, a1 squared. Over here, you'll notice I get a1 plus b1 and a1 squared. But when I multiply that in, c times a1 and c times b1, that surely is the same, right? Ooh, this should be a b1. I'm sorry. That should be b1. Those are the same, but when I multiply my scalar here, I don't actually have c squared, I just have c. Therefore, they don't work either. Tricky, all right? I know this is a little bit complicated. Let's just roll with it. See how we do as we get going. All right, let's take a look here. So we have function f is the following linear transformation. So we're going to take some coordinates and we're going to transform it with a 3 times our x plus 2 times our y. And then our second transformation is 3 times our y. And it's going to result in a vector of 2, 3. So in other words, we're going to take a matrix. We're going to multiply it by another matrix. And the result we know should be the matrix 2, 3, which represents the vector 2, 3. So first thing, let's look at this. Let's go back. Let's go back a little bit more right here. Let's relate what we found here as our transformation to our matrix. So in other words, if you look at this carefully, we have an x and a y, right? So in my very first input, I have negative x plus 0 y's. Down here, I have 0 x's plus 1 y. All right. Now let's go back and relate that to what we were just talking about, our new problem. Forward, 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 and boom. So we have our first one. Our first transformation is we have 3 x's and 2 y's. And then we have 0 x's and 3 y's. All right. And we don't know what our vector is that's going to result in this. We don't know that. All right. So we're going to do some multiplication. Now we're going to do calculator active right now. You need to go in, maybe pause the video, and put in your matrices, a 2 by 2 and a 2 by 1. All right. So A is going to be our 2 by 2 and B is going to be our 2 by 1. Okay. So pause the video if you need to, and then come right back. So I have this matrix times something I don't know, an unknown, to equal this matrix B. Now let's think about this. If I had the same equation, let's say 2x equaled 4, I would do the inverse of this, right? The inverse, and I would divide, right? 1/2 times 4, which is dividing by 2, 1/2, right? So this is the inverse. So I'm going to do the same thing. I'm going to have my unknown here, and I'm going to do the inverse of A times B. Now we know the result should be a 2 by 1. So let's be very clear here. This here is a 2 by 2, and this is a 2 by 1. I did it in a very specific ratio, right? Or, excuse me, pattern, because these have to match up, and it results in a 2 by 1. Let's say I did B times A inverse. That'd be a 2 by 1 times a 2 by 2, and they don't match, so we cannot do that, all right? So let's go back and see what we get when we multiply the inverse of A times B. So I'm going to do A, use my inverse right here, times B, go back to my matrix, And now I get the resultant of 0, 1. So my resultant matrix is 0, 1, which means my vector is 0, 1. All right? So you can make sure you can use your calculator on this, but that's how that's done. What transformation times what vector equal to my resultant vector, and we found that to be 0, 1. So if we did vector A times 0, 1, we would get 2, 3. Alrighty? All right. Best of luck. Dream big. Ask lots of questions. Until next time. Peace.